Hello everyone and welcome to new discussion which is on part 7 of GIS analysis, and we will continue as mentioned earlier in the previous lecture about related with this network analysis with few different examples, more realistic examples as well. As you can see that in normal cities or that kind of setup, we are having different kind of networks. There may be network like this streets network. There might be a rail station, there might be metro station, and several such networks may be there along with your power network and other things. So, a street, like if I take the example of a street, that feature class that can act as an edge source. So, that is one of the source or one of the elements of network. Then a street intersection features class acting as a junction source, the second element of network. And then the third, the additional line feature class as an act as edges, rail and also the point feature classes that act as junction, that is rail station or bus station. So, if every information is residing on your GIS database, then lot of analysis related with optimization of routes or monitoring of traffic and other things can be done very easily. Not only that, but also for planning. That means if it has to be done for planning, a prediction has to be done, and the prediction can also be done employing GIS. Now, in network analysis, as you know that resources or sources are there, all feature class that we have discussed so far, and they reside in the feature database, and that is our GIS database, especially the vector one and attributes also, and which contains the network data set and can participate as network resources. Now, if some because there are also nowadays a custom design GIS softwares or solutions are there. For example, your this Ola, Uber apps, these are custom designed GIS solutions. Similarly, you are having Google Map, that is also a custom designed GIS solution. So, for because there are different types of data sets or type of databases which are suitable for certain kind of analysis. So, when we will discuss the different types of databases, at that time it will come along with the relational database model, which is the most popular one. We also require hierarchical model sometimes for certain kind of analysis, and we also require a network database. So, in network database, the organization of the data, storing of the data so that these can be retrieved efficiently is different, and all these feature classes like junction and edges, these have to be also stored very distinctly within the database, so that a better route optimization can be performed. And only two sources can participate in a shape file network or a vector network data set, that is a line and a feature class or turn class. That might be a point in that sense also. Now, in network analysis, there are system junctions are there, and this which exist at each end of an edge in a network data set. So, wherever these things are there, then there will be a junction or a terminus also, you can say. And then if a junction source feature is not created at the end of an edge, that means a polyline feature, a system junction can be created automatically when the network data set is built. So, once your polyline data is ready of a network, then network has to be built, and that while building the network, then these things will also be created. Sometimes automatically, if it is a very simple network, then we can do it automatically through software, or with human interventions also. We have to guide the system that this is my junction, you have to define all those. But in natural drainage system, it can be done automatically. which will be demonstrated in the software as well. So system junctions are stored as point in a source feature class, which is automatically generated during the first build operation. And this source feature class, because every time you don't have to do it. Once a network is ready, then only then optimization or modeling will be done. So the source feature class is named as network name, and then you are having junction where network name represents the name of the network data set. And so likewise everything is organized in our network database. And when network data set is created, and then the user will make choices that determine which edges and junction elements are created from source features. It will depend on what kind of resources are going to move or are moving through that network. So based on that, then edges and junctions will be defined. If it is a rail network, a different kind of definitions would be required. If it is a road network, again it's a different. If it is a power supply network, again it is going to be different for edges and junction elements. And we have to ensure that edges and junctions are created, formed correctly, because then when we run for optimization or resource movement, then it should work properly. So accuracy part is also very, very important for network analysis and reliable results, because if we employ any system like GIS, any technology like GIS to get solutions, say about this resource movement, and then it has to be accurate. If it is not accurate, and if you say to your higher ups, maybe, could be, something like that, then there is no use of developing such system. So basically whatever we develop on GIS platform for any kind of analysis, it has to be highly reliable and accurate. So this accuracy part must be always kept in mind, and that is why since beginning I have been telling that one of the rules of GIS is that after each and every operation, check for errors. That means if we find the errors, we have to correct there itself. And if we follow this rule, so from the beginning of developing GIS database and analysis, then we can achieve high accuracy. So accuracy is also a key in GIS. Apart from precision, precision is a different thing. When discussion will come, we will have a lengthy discussion on these two terms. But for time being, what I am talking about, the accuracy. And because if results are not accurate, through whatever the analysis you have done through GIS, if they are not reliable, nobody can use it. I heard some time back a statement by an expert who was working on landslide hazard zonation mapping. And when he was asked that how accurate your map hai, so he said 50%. See, 50% probability means basically no prediction. I can predict anything that it may occur, may not occur. For example, I can say in next hour rainfall can occur, may not occur. So no use of employing such systems then. Anybody can predict. So accuracy has to be as far as possible to the highest level. And then only people will develop confidence in your system. Otherwise, people will discard immediately. They say it is useless. So, and that can be maintained from the beginning once we start doing anything on GIS. Now in network, the another important thing is the connectivity. Connectivity between different polyline features or different edges, if we talk in terms of network elements, and which are based on the geometric coincidences of endpoints, line vertices and points, and applying connectivity rules that set as properties of the network. Connectivity rules can be one-way traffic, two-way traffic, the flow conditions, the depth, the width, all these can come as attributes, and they also may become part of our connectivity rules. So let me take some example here. This is a connectivity network analysis, begins with the definition of connectivity groups. And what are these groups are, as you can see here, the connectivity groups are that I am having here the groups are that I am having a metro line, and then street, and then another group is, and the number 2 is having metro line and metro entrance, because they are part of that group of metro line, whereas the other the street and metro entrance is again because metro entrance will be used, it should be connected with the street. So, they are in the group. So, the connectivity analysis which begins with the definition of connectivity groups. And as I am just telling you that in this left diagram also, as you can see that these things are connected. So, detailed information is required before we really get the accurate results. So, this has to be created, this has to be defined to the database that which features network features belongs to which group, and there may be the same feature like road or this metro entrance is common for metro line as well as for street. And similarly, metro line is common for metro, of course, and the metro entrance. So, each edge source is assigned to exactly one connectivity group, and each junction source can be assigned to one or more connectivity groups, as you have seen here also. So, these are the connectivity groups. Now, the connectivity groups can contain any number of sources. So, here we can have as many as we can have in this connectivity group, the number of sources. Now, how many network elements connect will depend on which connectivity groups the elements are in. For example, two edges created with the two distinct source feature classes can connect if they are in the same connectivity group. As you have seen that like metro line and metro entrance belongs to the same connectivity group. Similarly, street and metro entrance belong to the same connectivity group. And if they are in separate connectivity groups, these one which I have just mentioned, then the edges won't connect. And if that has not been established, then this network analysis will not will work, because unless they joined by a junction, then participate in both connectivity groups. That means there has to be a junction between metro entrance and metro line. Similarly, there has to be a junction between street and metro entrance. Then only you can have a proper network analysis. And connectivity groups are used to model, because basically what we are using GIS ultimately many times for predicting something. Predicting, in this case, resources moving through a network. So, model multimodal transportation systems. Here multimodal, in this particular example, one is the road transport, another one is the transport which is metro. And as you know that for each connectivity group, like here, one select the network sources that interconnect. So, if somebody is analyzing the road or metro, accordingly then analysis will be done. And in case of the subway and street multimodal network examples below, here the metro lines and metro entrance are all assigned the same connectivity group. This part we have already discussed, that metro line and metro entrance are assigned to the same group, whereas street and metro entrance are also assigned to the another group. So, that is metro entrance is also in the connected group. So, that means that the one single feature class can belong to the two group also. This is the main point here of discussion. And once that is there, then it will form the link between two connectivity group. So, here these two features are like street and metro line, and which is here, and your metro entrance. So, these will link to each other, and then one can properly analyze the network. Now, any path between the groups must travel through a shared metro entrance. That means if there is another group, then again it has to be connected, then only it will work. So for example, a route solver may determine that a pedestrian's best route between two locations in a city is to walk on the street in a metro entrance. And there may be a broad subway train, take another train at line crossing stations and exit through another metro entrance. What it means that if in many cities, big metros, where they are having multiple lines and like orange line, blue line, green line, if we are talking only about the metro, and there may be at different levels underground. Now one can travel in one particular colored line. Colored are used just to make it convenient for people to remember. So from one line we can travel to another line. So we may not be coming out of entrance or metro entrance, but we will be moving within that one. So if a network analysis has to be done for, or that database has to be developed for such kind of resource movement mobilization in a metro system, which is a little complex in our example, then that much of details are also required. That from where, from which network or metro network, which line a person can come and to which line it can go. And you might have seen, I have seen that at some places there are having 4 lines, 4 colored lines on a metro station. So it's a really very complex kind of network, and it has to be properly managed, and that can only be done if the database, network database, and then connectivity groups have been created properly. So that connectivity groups basically will keep the two networks distinct, means yellow line, green line, something like that, and though they are connected through the shared junction or metro entrance. This is the point which is very, very important. So in many other resources also, many other types of networks, similar kind of issues will come. And if we want a very efficient network system, then all that information has to be organized in a GIS database, especially for the network analysis. Now, if we take this connecting edges within a connectivity group, how they are connected. So here edges in the same connectivity group can be made to connect in 2 ways. The first one by set of connectivity policy on the edge source. If one set endpoints connectivity, the line feature becomes edge, joining only the coincident endpoint. Like here, which you are seeing one junction, 2 lines are there. Several times in a metro maps of different cities, you may find that 2 lines are crossing, but there is no junction. Junction means here that you cannot disembark one line metro and go to the another, though on map these are being shown. So if that thing is not there, that information will not be stored. But in this example, that is there, that a junction is there of 2 different lines and it is kept there. In this example, though there are 2 lines are crossing each other, but there may not be any junction. So that kind, those details are very much required. So like in this case, the line feature, this L1, or you can say, this it should have been J1. So the line feature J1 becomes edge element of E1, as you can see, and the same L2 or J2 becomes the edge feature of E2. So this is also E2. So the one is this line, another one is this line. And there will always be one edge element created for one line feature with this connectivity policy. So depending on the conditions, then only things will be organized. Now we continue on this that connecting edges with the connectivity group. So building networks with endpoints connectivity is one way to model crossing objects such as bridges. Now there are over bridges or underpass are there, and so if we want to keep that kind of information, if that is required, then that information has to be also built in our network analysis or network database. And we have to model, that means to predict and organize the two sources, bridges and streets are placed in same connectivity group. Then only these things can be used in GIS. So, if any information has to be utilized, it has to be residing in our network database, otherwise it cannot be utilized. So, it's a very simple in that sense, that if we want to have the information about bridges, underpass, overpasses, flyovers, that information in case of road network, that information has to be there. Now, in case of street source is assigned to any vertex connectivity, which will allow to a street feature to connect to other street features at coincident vertices. Coincident vertices basically are the junctions. Coincident vertices will make the junction. In case of road, it is a little simpler in that sense, because in case of metros, sometimes metros are running at different depth in underground conditions. Now, if we see that like example is given here about the bridge, and there is another bridge is here, the bridge is there, but between these two bridges there is no connection. So, then there will be a problem. So, the bridges source is assigned endpoint connectivity, and these are creating a endpoint here, and this means that bridges connect to other edge features. So, there is one edge feature like here, another edge feature like here, and that other edge features, and what will happen consequently, any street going under the bridge will not be connected to the bridge, and the bridge will connect to other streets at its end point. So, then incomplete network, and if that kind of error is there, obviously any kind of modeling or any kind of management will not be possible. So, accurate development of accurate network database is of prime importance in case of network analysis. If there is only one source in network, then overpasses like bridge, underpasses, tunnels can also be modeled by considering elevation fields on planar data. That means if there is a change in elevation, because underpasses, overpasses will have one line is going over some line, and then the depth information has to be also stored, like in case of metros, in case of overpasses, tunnels and everything. So, that much information will be required to be stored. And now, further in this, that if user set any vertex connectivity, like here the vertex connectivity, in previous example we have not seen the junction 3. Now, when it is connectivity and split into multiple edges at coincident vertices. So, once a junction has been created, now these are splitted. Earlier there were only one like and like this. Now, we are having 4. So, there are 4 edges because a new junction has been created. Now, if this junction is at the same level, then there will be different issues in case of road transport or other thing. But if there are different levels, then the sideways or other things have to be provided, and from traffic management point of view. So, that information will also be required to be stored in our database. So, setting this policy about creating junctions is important if street data is structured in a manner that streets meet other streets at the vertices. But if it is a junction like this, but as I have said, if junction is having 2 different levels, then there will be a different scenario. So, in this case 2 polylines crossing at a shared vertex position are split into 4 edges with a junction at the vertex. This is what you are seeing, the J3. So, junction at the vertex is there 3 in this example. So, edges E1 and edges E3 has with the source feature class object ID is feature, and that is J1. So, that is the J1. Similarly, for other edges also similar way it has can be defined. Now, edge E2 and E4 are identified with the source feature class and object ID of that is the J2, which is this one. And the junction J3, which we have been discussing, will be newly created system junction. So, this system may create this one depending on our information, and then we will have the junction J1, J2, J3, J4 and J5. So, 4 are the end vertices and one J3 is the cross vertices, and that is truly a junction, otherwise these are the terminals. But anyway, in network analysis point of view, these are also called junctions because they may have connectivity with other network. So, that is why they are called junction, or this is the junction from coincident point from a source feature class. As you know that not all crossing line features are produce connected edges. That means there may not be junction in all the cases. And if they do not have these share any coincident endpoints or vertices, no connectivity policy will create a junction at that point. So, it depends on the how your network is there. If there is a junction which is required, which can be created, if not, that also can be avoided. So, street data of that much with that much attributes have to be required for network data sets, and which must be cleaned first so that it can be retrieved efficiently. And clean here means accurate and having good quality of the data, cleaned here. So, if it is not, then it has to be organized first, then only any kind of modeling or operations can start. And to overcome such street data, either a geoprocessing tool like in GIS, which are available like in ArcGIS, which can integrate to split the crossing lines or establish a topology on these feature classes and edit street features with while applying topology rules that enforce feature split at junctions. Now, automatically these things cannot be done for a say road network or power network or rail network. So, that means human interventions would be required to declare that which is the intersection, which is the junction, which is the edge and so on and so forth. And therefore, among other GIS databases, the network database, when we will discuss in detail what is the exactly network database is or advantages with that or disadvantages, this is the most complex database generation. But once a accurate network database has been generated, then one can really exploit extensively and can have lot of applications on it. Further on the same discussion that edges in different connectivity groups can be connected only through a junction shared by both connectivity groups. So, here like here this is not connected by any other group, and this also the black circle, that is though maybe a junction, but not shared by any other group. Only one which is connected is this one with this the thick black line and grey line, and another one is like this one, which is relatively thin line. So, two networks are there and likewise. So, in this example, a multimodal system combining a bus network, a street network, a bus stop is added from the end source, from a point source and in both connectivity groups. So, by creating a junction, you can connect two different systems, multimodal systems, and a point location for bus stop, and then be spatially coincident with the bus lines and street lines also. Bus stop cannot be created away from a road network. How in database it will be reflected? Here see, as you can see that bus stop is marked here, and then you can have a policy that it has to be honored. That means it is very much required, and whereas a bus line, it is the end point of within our database. So, against basically each polyline feature, this detailed information is required in our network database. And when the point location and like endpoint for the bus stop is added, whether it successfully becomes a junction depends on the junction connectivity policy. And these policies which I am talking is not policy made by some administrations. These are the policies within your network GIS database. So we have to define policies that how these junctions or other multinodal systems will work. And as with edges, junctions connected to edges at endpoints or vertices, and this will depend on the target edge source connectivity policy. So, lot of declaration to the system has to be done that this is what I want, this is what I do not want, and that becomes basically our policy. So, there may be a situation in which you might want to override this behavior or this policy, and that can be also changed because everything in a digital form, so it can be changed. Now, when you go for creating this thing, there will be options available in a good software. Like here it is saying honor or override. So, if you want to honor that policy, that what is that policy is the connectivity policy, you can choose accordingly. So, for example, the bus line that the bus stops connects to has an endpoint connectivity policy, but often one will want to place the bus stop at an intermediate vertex. So, you can also if it is in planning stage, that can be done, that you do not want bus stop at the end, you want bus stop before that also. And in order to achieve that one has to set a junction. So, a junction policy has to be required which will override the default behavior of connectivity junction to a given edge, and then it can be done. So, a override default behavior of junctions forming a endpoint or vertices according to the edge resources connectivity policy set the junction resource policy to override, and this is what it is being done here. So, depending on our requirements. Now, when we bring the elevation part, means there are different levels, then things becomes more complex. So, very briefly we will also discuss this part, that the connectivity of network elements can depend not only on whether they are coincident in x and y space, that is in horizontal space, but also whether they share the same elevation or not. I gave the example of different metro lines at different levels, at least at the junction. Away from junction, they may not be at different levels, but at the junctions they are maintained at a different levels, and 3-4 lines can be at a one junction, and therefore people can use different levels, elevators to reach to those levels and to get different colored lines. So, there are two options for modeling elevation or different levels using elevation fields, that is the Z value from our geometry, and that is very much required if such scenarios have to be developed or such modeling is required. If there is different levels, the elevation Z value is very much required. So, elevation fields which can be created in a database are used in network data set to redefine this connectivity as line endpoints, and they contain elevation information which is derived from the field on a feature class participating in the network. So, the height above mean sea level or depth or whatever information has to be collected, and then it has to be stored in our attribute table as a feature class participating that in network. And this is basically the different from establishing connectivity, which is not basically, which is based on Z coordinate values, because so far what we have been discussing when we did not involve elevation was only in the xy plane, means so everything was considered as a planar or an horizontal. But when there are upheavals or different levels, then different this policy or connectivity has to be established which will incorporate the Z values. And basically these are the physical elevation information which is stored for each vertex. Like in GIS nowadays, earlier we were told that a point is just having xy and it is a point, but now in literature you may find, or in some software they say 3D point. Now by definition vector is a vector element, this point is a 0-dimensional entity. So how it can be 3D? So basically what we are adding, the Z value. Now that Z value can come automatically in our GIS database for any given point, either from a digital elevation surface like DEM or some other field data based on GNSS data collection or some other topographic survey. So that point, though it is called 3D, but it is not exactly 3D, only it is having location xy and also Z value. So when we are doing this modeling or incorporating elevation for a network, then for each vertex that information about elevation will be very much required. Though our network database may become little complicated, but it will be more realistic. Then only people will adopt it or use it or appreciate it. Otherwise, you say no, you have to assume everything and as a planner only an XY, then no use of such solutions through GIS. And therefore, elevation fields apply to edge and junction sources as well. Once for each vertex, once you have stored, then vertices are part of edges and junctions also. And edge feature sources using elevation fields have two fields to describe elevation, one for each end of line features. Because a line, if a polyline may have different elevations. So if suppose it is having 100 meter above mean sea level, it is having 110. And therefore, for each vertex, elevation information has to be stored, and here if the line feature for the each end member and that end vertex, that information has to be stored. Then you can get even the slope information as well. So like here in this example, a very schematic and simple example, that 4 line features are there, that this EF1, EF2 and EF3 and EF4 element features, and you are having these 4 line features belonging to the same connectivity group. So there is a basically junction defined. So coding has been done for this is 0 connectivity group, and this is 1, blue is the 1 connectivity group, and which observe endpoint connectivity is also shown here with the junction. Now elevation values at like for example F3 and F4 may be 0, and whereas elevation values at F1, EF1 and EF2 are 1. For simplicity these things have been kept like this. So that means now this junction, if it is junction, it is at 2 different levels in terms of elevation. And then this intersection, the point of intersection of EF3 is connected only to EF4 and not to EF1 and EF2. If it is metro line, and those 2 lines I mentioned earlier also may cross each other, but on a plan or on a map, on a 2D map. But if they are at different levels, then they may not be connecting, there may not be intersection or there may not be any junction. Now if junction has to be established, then in say subways or in case of underground metros, then within the this underground conditions, that junctions has to be created. So therefore people from level 0 can reach to level 1. Now further in this that same with the EF1 connects to EF2 only and not to EF3 and EF4. So it is true for both type of network here, and it is important to understand that the elevation fields define connectivity, they do not override it. Because in your policy, you cannot instruct the system to forget about elevation. No, when you are dealing with a system which is also having elevation information, then that cannot be overridden. And two edges elements may have the same elevation field values, means on the edges they may have same. And this I have also mentioned that different networks, except for at junction, if they are connected, may have different elevations, but at a little away from junctions they may not have the same, they may not have different elevation, they may have the same one. Because this is how in metro systems, this is how it is developed. So, two edges elements here we are having like these red and blue lines may have the same elevation field and may be coincident, but if they are placed in two different connectivity groups, they will not be connected also. So, even if they are on the same elevation not connected, then they are not connected, so simple. So, numerous data vendors or provide elevation field data to model connectivity. In case of ArcGIS network dataset connectivity model, one can use this elevation field data to enhance connectivity or basically to make more realistic network analysis by involving elevation field if it is required and if that information is available. If that information elevation is not available, then of course real scenarios cannot be prepared. So, the interaction of elevation fields with the connectivity model is vital to model spatial scenarios such as bridges or tunnels. Further, various available digital elevation models can be used in elevation field data to model connectivity, but only in case if things are moving on surface. But if you are having subsurface conditions like underground metros, then digital elevation models cannot be employed. Then that elevation information has to come from other sources. So, interaction of elevation fields in our network database with connectivity model is vital to model these bridges and other features. Now, how these things are organized, which we can understand through this 3D perspective view, that we are having z coordinates value from a geometry. So, this is a 4-line feature are shown in 3-dimensional space and 3 horizontal lines are there, 3 horizontal lines. This is though it is looking inclined one, but in only through this, but you can see that this is also horizontal and the other one and this one. So, the 3 horizontal lines the blue line, this line and this blue line, and one diagonal line which is the red line in this model, and 6 green spheres which you can count here, they are there, which are representing the end points of each line. Now, the same we can rotate this graphics once it is in computer, that this graphic shows the same lines and end points from another perspective, and it is very clear that there is no connectivity of this blue line with the red line. So, it is clear that red line connects with the top 2 blue lines, these top 2 blue lines and their endpoints, yet the red line does not interconnect with the lower line. So, depending if when we are working in a 3D or for subsurface transport system, then in one perspective view, we may feel that there is a junction like here. But when we change the viewing angle, then we see that no, there is no connectivity at all. So, depending on our requirements basically, these things have to be organized. If a junction has to be created, then in subsurface condition, excavation has to be done and then a junction will be created here. So, and then connectivity. So, when source features have z values stored in their geometry, one can create 3-dimensional networks like example here given. And indoor pedestrian means in subsurface conditions, in underground conditions, paths are often modeled with 3D. And consider that many hallways in a multi-story building, like nowadays lot of huge malls are also coming there also connectivity has to be established with these escalators, with lift and pathways. So there also it will be very much required to bring this like elevator, shaft, connect floors. Everything has to be stored in a system, all detailed information, and if that is done, then we can have this the z coordinate values in our geometry. If that is available, then only a nice network can be established. So, like here we are seeing that there is no connectivity between blue line, this E3 and E4, though this red line is meeting with junction 2 of E1 and E2. Now, that means they are at different levels, the red and this blue, these E3 and E4 are at different levels. But if we see in a different perspective, they may look. So, if we want the connectivity, then junctions are required. Like here, one red line feature intersect with the two blue line features, the top one and the bottom one. And since the lines connected at vertices, their corresponding edges may or may not connect. A network data set depends on the connectivity policy. So, that much information is required when we are dealing with the z coordinate. So, things becomes really complicated, but if everything is organized, elevation informations are kept in our database, then 3D analysis can be performed very easily using network. It will take a lot of time to develop a network database and a GIS platform, but once a accurate network database has been developed, then we can really model or monitor or manage our movement of resources or mobility. So, with this I end this discussion. Thank you very much.